Lesson one. Maybe you could make an argument the most important discovery of the last 200 years. Voltage induced by motion. In the previous unit, we learned that when electric charges move, they produce a magnetic field. That was the first right-hand rule. And that magnetic field will exert a force on other moving charges. That was our right-hand motor rule. Early in the 19th century, scientists such as Michael Faraday and Joseph Henry were aware of these properties, and they both asked the next question. Well, look, if a current can produce a magnetic field, can a magnetic field produce current? Can we use magnets to generate electricity? I'm going to give you a note here. Electromotive force, and I know it contains the word force, so it's abbreviated as EMF because it's not measured in newtons. Its symbol is this curly E. It's an archaic word that refers not to a force, but to the voltage of a cell. This is going to be the same as this. And in this unit, often I'm going to use this as my symbol for voltage. And the reason is often we're going to have a lowercase v for speed in the same equation as V for voltage, and it gets confusing. So you're going to start to notice I'm going to talk about an EMF of voltage. Typically, when we're talking about an EMF of voltage, we're actually meaning an induced voltage, a created voltage. So V and EMF mean the same thing, and they're going to be used interchangeably. If a piece of wire moves through a magnetic field, the charges in the wire will experience magnetic forces. Since the electrons in the metal are free to move around, but the protons are not, the negative charges will move to one end. We're still going to pretend that the protons are going to move. We're going to use the right-hand rule to figure this out. So here I have a wire. Kyle, what direction is the magnetic field according to this? It says on the right-hand side of the diagram. What direction is the magnetic field? Okay, into the page. What I'd like all of you to do, just put a single proton in the middle right there. We are pulling this metal bar by hand, physically, through a magnetic field. So let's just target one charge. What direction is that proton moving? What direction is the velocity arrow? So everybody point your right thumbs down the page. What direction is the magnetic field? This diagram has become corrupted. There should be X's, and I just haven't had a chance to fix it. What direction is the magnetic field? Into the page. What direction will the protons feel a force? To the? Jaya. What direction will electrons feel a force? To the? Here's what's really going to happen. What's going to happen is one end of the bar is going to become negatively charged. One end of the bar is going to become positively charged. What you've just done is you have separated charges by doing work. You've technically created a voltage. You've induced an EMF, a voltage, because you've made charges separate from each other in the same way the chemical reaction of a battery made charges separate from each other and then sent them through a circuit. So since charges have been separated, which takes work, we have voltage, because voltage was defined as the amount of potential energy per coulomb. It was defined as work per coulomb. I spelled Coulomb wrong. It's C-O-U and then O-M-B. Mr. Coulomb would be offended. Okay. In fact, you would feel a force resisting you because you get nothing for free. Otherwise, that would violate the conservation of energy. It would feel strange as you were pulling this bar through the magnetic field. You would feel a tug in the opposite direction. We call this voltage induced by motion, motion voltage, or induced by motion voltage. Induced voltage, because the energy, Emily, in this case, comes not from the chemical reaction like in a Duracell battery, but from motion. In other words, movement, motion, can induce an EMF, a voltage. That's very important. Let's find an expression. Well, first of all, V equals, we're going to start off with the definition of voltage. It's going to be work per coulomb. potential energy per coulomb, but I'm just going to say work per coulomb. Kenta, do you remember work is what times what? Our most basic definition. If not, look at your formula sheet. Okay, so I can write this as, now I'm going to start to put the wings on the V. You're going to see why in this. In fact, you know what? I'm going to stop writing the V and I'm going to start using an EMF symbol. If you put a V, just cross it out and next to it, put the EMF symbol. And you're going to see why in a second. Yeah, it's going to be force times distance over Q. Which force is causing this voltage to be induced? A magnetic force. So do me a favor, put a little subscripted B on the F. It's FB. Now, we're looking at the force on a moving charge. Kenta, what's the magnetic force on a moving charge? Formula sheet. Also on your test on Tuesday. No. There's an equation for the magnetic force on a moving charge. Formula sheet. Also on your test on. So, yeah. In fact, it's going to be QVB. The D is going to drop down. And instead of a big Q, I'll make it a lowercase q because, Kenta, what happens to the Q's? Yeah. Oh, see the lowercase v for speed? That's why I replaced the big V with the EMF symbol. Otherwise, you might be tempted to cancel out a V when you cannot. Have I mentioned occasionally we don't have enough letters in the, we don't. Okay. It's not really VBD. It's really typically written this way. EMF equals B. Instead of D, we use a lowercase l for the length of the bar or wire times V. And all three of these have to be at right angles. So I'm going to put little perpendicular signs beneath them. And if you notice on your formula sheet, that should be the next equation down after the magnetic stuff we just finished. I think it should say EMF equals BLV. Okay, it's a scalar equation. V or EMF is voltage induced by motion. It's often called motional EMF or induced EMF. And again, the reason we say EMF, initially when they called it electromotive force, they didn't really know enough about electricity. It's not Newton's. So I don't like saying the word force to describe this because it's not Newton's. And you may have noticed I'm hung up on units. Little. So we all just abbreviate it as EMF. B is your external magnetic field, maybe from a solenoid. So this B here could also be mu naught N times I over L. Different L, length of the solenoid, not length of the bar. L is the length of the wire in meters. V is the speed of the wire, perpendicular. You get your maximum EMF when everything is perpendicular. What if they're not perpendicular? Turn the page. You only get a very tiny amount of voltage. So here, the length is parallel to the velocity. Let's do the same trick as before. Let's put our little positive right in the middle there. Victor, what direction is that positive charge traveling? Well, it's inside the bar. What direction is the bar traveling? Down. So point your thumbs down, magnetic field into the page. And okay, it would try and get pushed that way. The negatives would try and get pushed that way. Are you going to be able to really separate the charges at all? It's too skinny. Doesn't work well. Okay. So, example 4, find the induced voltage across the ends of the moving wire and indicate which side is positive and which side is negative. So, induced voltage EMF is BL V, straight plug and chug. It's going to be B, 1.25 Teslas, pretty big magnetic field. L, 0.8. V, I guess it's going into the page. No, yeah, into the page, 5.25. If you put a voltmeter on either end of this bar, or if you wanted to pretend this was a battery, how many volts are we getting from this battery? Good to hear people finally getting out their calculators. Finally. 5 point, is it 5.25? Units, volts. Ooh, which side is going to be positive? Which side is going to be negative? Aryan, what direction is the velocity? What does that x mean? Look up. Yeah, sorry, you're what? And again, we're going to do the same trick. We're going to pretend there's a little positive in the middle. It's traveling into the page because it's locked in the bar. So everybody point your right thumbs into the page. Aryan, what direction is the No, don't curl your fingers. We're doing this one. I got to break you of that. As soon as you do this, you've introduced a 90-degree bend, and you might leave that when you do the magnetic field. You're going to get total nonsense answers. So it has to be like this. Or if you're doing the three-finger one, that's fine as well. What direction is the magnetic field? Tells you downward. So fingers into the page, magnetic field down the page. Which way are the positives going to feel a force? I think to the left, yes? I think this end is going to become positive. This end is going to be the negative terminal of your battery. Now, it's a moving battery at this stage, which makes it tricky to use in a circuit, but have patience. This was the first, hey, aha, we can create voltage with motion. Now we just got to be a little bit clever. One area this is used is in airplanes. An airplane is essentially a metal bar traveling through Earth's magnetic field. And you do induce a voltage. Now, first of all, what's the direction of the magnetic field? You can assume that at altitude, when they're way, way up there, the direction of the magnetic field is into the page. So if you want to, you can draw a little X like that. Which length am I going to use, the 60 or the 150? Your hint is, which one is perpendicular to all the others? The 60, because which direction is the 320? That way, don't use the 150. Okay? First of all, how big is the voltage going to be? E is going to be BLV. It's going to be 0.008. Mr. Dueck, I thought you said the magnetic field. Magnetic field is weaker on the surface of the Earth, but it's stronger up there. And it's also just not consistent. It varies as you get further or closer to the poles. Which L am I going to use, Joanna? And the airplane is going 320 meters per second. How many volts would you get across the wings? Marcus, what'd you get? Sorry, how many? 154? That's not a bad voltage. That's getting up there. My understanding is back in the 1950s and 60s, when everybody still smoked on airplanes, this was the voltage they used to power the little push-in cigarette lighters that would eventually get warm, heat up, and pop out. They used this. Why not? It's free voltage. Generating power on an airplane isn't that easy. May as well use it. Oh, which part of the wing would be positive, the top part or the lower part in our diagram if we're looking? Let's see. Point your fingers in the direction of the moving charge. Magnetic field is into the page. This side of the wing would be positive. This side of the wing would be negative. Ella, did I lose you? Am I right? Pink thumb that way because the airplane, right? We're always just imagining here's the proton locked inside the airplane. It's traveling to the right. What direction is the magnetic field? What does the X mean? Into the page. Yeah, protons are going to get pushed up. Electrons are going to get pushed down. Is that all right? Next page. So here was Faraday and Henry's first idea. They said, what if we take that metal bar and we lay it on conducting rails, so as we're pulling it, maybe now we can make it part of a circuit. In fact, the strip will act like a battery and will get current flow. So example 6 shows that the polarity of the moving strip or wire is like that of the cell to the... Let's see. Let's put, again, our little proton right there. Okay. Emily, what direction is the proton traveling to the, I'm looking for where that starts letter R, right? Ooh, what direction is the magnetic field? So, proton to the right, magnetic field out of the page. Which way will the proton feel a force? Down, yes? So, which way will the current flow then? Current will flow this way, because current is which way the positives would want to flow if they could. And so mathematically, it's very similar to if I had a battery with the positive end pointing down. If we had a little resistor right here, if it was a light bulb, as soon as we started to pull on that bar, the light bulb would start to glow. Okay, now we're getting a little closer to what we want. We're at least doing something. Problem with this system, of course, is, well, what happens when you run out of conducting rail? You have to lift it up and put the bar back at the beginning and start over. Ugh. But okay. Also, though, if there is a current flow through the moving metal strip or wire, there's also going to be a magnetic force that can slow it down or speed it up. Let me show you what I mean. So we all agree that if we pull this bar to the right, Taya, protons are going to move down, yes? Okay, but now we have protons moving down. See the current? Now point your right thumbs in the direction of the current, which is down the page. What direction is the magnetic field still, Ashley? What direction is the magnetic field still? So, thumbs down, magnetic field out of the page. What direction will the bar feel a force as soon as current starts to flow when you're pulling on it? What direction will the bar feel a force? To the? There's going to be a net force this way, and it would be very strange. I'll call that FB. You would feel this something tugging on you. You would be going, wait a minute, how come this bar suddenly got tougher to move? It's because as soon as you started charges moving, now not only are they moving sideways, they're moving down. That's another right-hand rule. It's also a consequence of conservation of energy. You get nothing for free. Because the other possibility would be that the force could be to the right. Well, then it would just speed up magically on its own. That would violate the law of conservation of energy because it would be gaining kinetic energy from nothing. If you've ever used one of those rechargeable flashlights where you turn the hand crank, they're not very easy to turn. It's not because they're badly designed or there's lots of friction. You are feeling that force. You are starting some charges moving, and as soon as you do that, also it turns out there's going to be a magnetic force resisting what you're trying to do. That's what you're feeling. So, example 8. The strip below is 12 cent. Nice try, Dueck. 0.12 meters long, moving at 4.7 meters per second, not very fast. But external magnetic field is 0.08 teslas, and the resistance, of the rail circuit is 0.025 ohms. Find, okay. Taya, what does A want me to find? EMF equals BLV. It's going to be 0.08 times 0.12 times 4.7. What do you get? I don't think this is going to be a spectacular voltage. These are pretty small numbers. Okay. Taya, what does B want me to find? What did I just find? Voltage. Is there an equation that has current and voltage in? Oh, V equals I times R. Get the I by itself. You know what? In our notes, let's write it. V equals I times R. So I is going to be, and instead of V, I'm going to put EMF because it's the induced voltage divided by R. It's going to be 0.045 divided by, they did tell me a resistance, I think. I hope, did they not? 0.025. What do you get? Oh, 1.8 amps. That's a little, okay, that's substantial. 1.8 even? Okay. C. Let's keep going. What does C want me to find? Okay, FB. This is, I think this is a wire. So I think we're going to use Bill. Also, because what did we just find in part B? Current. So not QVB, not for a single moving charge, but for all the charges in the wire. And so it's going to be the magnetic field, which was 0.08, I, which was 1.8, L, which was 0.12, .017 newtons. It's a force. Faraday and Henry asked the next question. They said, okay, what if instead of a bar or a single wire, what if we move a loop of wire? What will happen then? Do we still get induced voltage? Do we still get induced current? So I'm going to treat this like 4 separate bars. Put a little positive proton in the middle right there. Put a little positive proton in the middle right there. Put a little positive proton in the middle right there. Put a little positive proton in the middle right there. Okay. In the top one, we would have the proton moving to the right, magnetic field out of the page. Well, the top one, in the top one, the proton is going to get pushed down, but are we moving parallel to the magnetic field in that top, or to the velocity in that top one? There's nowhere for the charge to separate. So in this one here, there's just nowhere for the charge to go. It can go to the bottom of the wire section, but that's not much of a separation. And the same with here. So even though I wrote those, you're not going to get much happening there. But the front one is more interesting. Let's look at the front little section. Yeah, Brandon, that way, magnetic field out of the page. What direction will the front bar, will the protons in the front bar feel a force? Yeah, so let's draw a little F that way. Well, instead of F, you know what? Let's scribble that out, current. That's which way the current would flow. You okay with that? Ooh, what about that bar at the back? Well, proton is still traveling to the right, magnetic field out of the, which way will it feel a force? Can you see what's going to happen with these two opposing currents? They are going to cancel each other out. So sadly, opposing currents cancel. We get nothing. Ah, rats. Okay. We'll come back to this loop idea in a couple of days. But if you turn the page, now we're going to ask ourselves, look, instead of us supplying the motion to get voltage, what if we supply voltage? Can we get motion? This is the physics of a railgun. But we're going to pause here. So on Monday, we're going to do a fun activity. Tuesday is your test. Wednesday, we'll pick up with this. But I thought that was also lots of nice right-hand rule review. I thought that was good for you for your test.